Okay, looks like everybody that's here so far can hear me. That's a good thing. Let's see who we're missing. Yeah, the usual culprits are not here. Okay. Unfortunately, some of them are the people that need to hear the next couple of sentences, but I'll go ahead and talk about them anyway because we've got a lot of material to cover tonight. I looked at the exam 0 that you submitted to me, and almost everybody did it right. Almost. We got really close in this class. There were still a couple people that attached them as OneDrive documents. That's not what we want. You want you to attach it to the email. So a couple people that did that, one of you corrected it, the other one, I sent you an email, but you didn't do anything about it. Somebody named their file wrong. Name it exactly what you download. No different than that. Don't be creative. That's the wrong time to be creative. And other than that, some of you even got the questions right. That was surprising. Now, when I give you the exam on Monday coming up, you will, when you turn it in, receive from me, and actually not from me, it's from Tom, but you'll receive from us a thank you note. It's just basically an email coming right back, reply to your email, which says thanks. That email is the only thing that shows that you successfully submitted your exam. If you haven't gotten that back and the clock runs out, time runs out, then your test will be late. So you need to make sure, unless of course we're backlogged, and then we'll add a little bit of time at the end of it. Because usually what happens is everybody submits it to the last minute, and then they've got to do 20 things. We have to do more than just see the email. They actually check to make sure that you did attach a file. They check to make sure that the file looks like it could be processed. A couple things that would save you some problems later on. But make sure you save that when you get it, because it's the only thing that's your receipt. The fact that you have a thank you note is the only thing that says we got it. Us having it doesn't make it you have it. Us or you thinking you sent it isn't good enough. You actually have to get back the receipt. And we'll work out the procedure and the process around that to make sure that everybody does it. The other thing some people did, and you don't do this, is they submitted it twice. If you're going to have to submit it twice, make sure you check with me before you submit the second one so we don't process the first one. We're not going to process 2 of them. And chances are, if you submitted a second one, you think it's a better one than the first one was. So don't do that. Make sure you only submit one. Make sure you've attached it to your email, and make absolutely certain you're sending it from your Mercer email, not any other email. Anybody have any questions about the exam? Scott?
So in terms of Blackboard, we'll still go into Blackboard at the beginning of class to get our exam assignment. Then we'll go out of Blackboard to do the exam, and then we'll log back in at the end.
You only have to log back in if you don't get a thanks.
Okay.
Okay, so if the test takes you 10 minutes and you send it to us and we send you back a thank you, you're done for the evening. If it looks like it's going to take you longer than the allotted amount of time, make sure you stop a little bit before the allotted amount of time so you'll get it turned in on time. You'll lose points if it's late. And those of you, I don't know if anybody in here has them, but occasionally the school will give people accommodations, which means that for some reason they need more time than the rest of everybody. I don't get it either, but they do. And so we have to honor that. And so if you have a time and a half and we give you an hour, you get an hour and a half. So at an hour and a half, you make sure you've sent it in and that you've gotten a thank you back. If you have double time, which means you get 2 hours on the exam for every 1 hour, at the end of the time, you make sure you send it in and you get it back in time based on the time you're supposed to be done with it. And make absolutely certain, particularly if you have an accommodation, that you don't contact or talk to anybody else in the class who may have already finished the exam. One of the things I'm not going to talk a lot about this semester, because I just expect it from you, is that you have academic integrity, that you will not allow anybody to cheat off your material and you won't cheat off anybody else's. In the long run, you will wind up doing much better with me, but you'll do better in the course if you don't do that. Because if, for example, on an exam you can do something, but then in class I ask you to do it and you can't, that's awfully suspicious. Yes, sir, Robert, you have a question or comment?
Yeah, will we be receiving any kind of feedback on the exams? So there were a couple on there that I felt a little lost.
Not on the first exam, not on the one you already did. Although, tomorrow night, did I tell you I was going to do a review? That's tomorrow night, right? Okay. Yeah, about 6 o'clock I'll get online. I might go over some of those questions. I might be able to be talked into that. But other than that, there won't be any feedback on that exam. Although those questions look like things you could expect to have on the exam that's coming up. And tomorrow, again, let me remind you, the review at 6, you can drop in for as long as you like, the whole period, part of the period, late, doesn't matter. You get no extra credit for being there, and you lose no points if you don't come. It's just completely optional, and it's just a chance for me to review the material, and some people might benefit from that. So if one person shows up, great, I'll have somebody to talk to. If nobody shows up, I'll still do a review, but it'll probably be a lot shorter. If everybody shows up, then we'll probably fill the whole normal class time. But we'll see. Because I realize some people have other classes, or you may work, or anything else could be going on. So I'm just offering it as something that, might be useful to you. Any other questions before we proceed? Okay, let me put this piece of paper over here. Let me see if I did that. Oh, yeah. Extra credit on the first exam. If you send me a picture of yourself, an image of yourself, a picture of yourself, before the exam begins on Monday night, I'll add a point to your grade. Now, a point doesn't sound like much unless you're sitting on the borderline between A and B, for example. So all you have to do is go find some good picture. Don't send me any picture that makes you look stupid. Send me one so I'll know who you are in case I ever see you somewhere. Let's assume I'm walking around with one of my business friends, and I see you and I remember you from class because I can see the picture of you and then see you. And they say, do you know anybody that's good at this? And I go, let me think about that class. Well, let me think of that. I come up and I say, I remember, yeah, Dante was in that class. That's Dante, isn't it? Let me introduce you to him. But if I don't have any pictures of you, I really have no idea who you are. And so, if you can find something, or take a picture, whatever, but to consider it to be like a picture you might put on a business resume, something that's reasonably good of yourself. It doesn't have to be formal or anything. It can be informal. But if you can send me that, I'll give you a little extra point on your first exam, which you might need, you might not need. Anybody have any questions about that? Yeah, Robert?
Is that an extra percentage point or an extra point?
That's a single point. Single point. Oh, I see what you're actually asking is, if you have an 88, will it become an 89 on the exam? Or if there's 10 questions, will it be 11 instead of 10? It's after they've been turned to a percentage.
Okay, so if you have an 89, that would push it up to
You have an 89, which is a B+. You get a 90, which I believe is an A-. Anybody have any other questions about that? Now, don't send me any scary pictures. I had somebody send me a scary picture one time, and I had to run out of the room when I saw it. And I think that's what they actually look like. But nevertheless, I didn't go back in that room for quite some time. I'm just expecting just normal people in this class, so don't disappoint me. Okay, everybody understand that? Everybody understand what I'm looking for here? Just a picture that I could use to recognize you if I saw you somewhere, and also to, that you could use if you ever wanted to include a picture with a business resume or something like that. Okay, Doug, well, that's enough of you that understand. Maybe not everybody wants to do it. And if you're too embarrassed to send me your picture, that's okay too. If you just you're too shy. Okay, let us move ahead. Now, there's a lot of lecture material tonight. Normally, we don't do a lot of lecture, but there's a lot of lecture in what we're going to be covering. Where we sit in this particular section is memory, programmable logic devices, FPGAs and ASICs and HDLs, and VHDL. Things about VHDL will not be on the exam, but there might be something about tri-state logic or the bus architecture. I don't think there's anything about memory or PLDs. I don't think there's anything on FPGAs or ASICs. So, you know, I would, if we did this last class, tri-state logic and bus architecture, make sure you're up to date on that. But these last topics will be on exam 2, which isn't too far down in the future. Okay, doke. Let me just minimize this. Okay, initially, let's just talk about memory for a second. There are really two main types of memory as we're going to divide them up. One is called RAM, which stands for Random Access Memory. And it's the memory on your computer where data can be written and data can be read. So it's bidirectional memory, and it's addressable by some memory address. It's not a sequential memory type, although I'm not even going to cover some of those variants. Random access memory can come in all sorts of flavors. We have something which is called static RAM versus something called dynamic RAM. The primary difference being that for static RAM, once you write something to the memory, as long as it retains power, it will remember what that byte contained. Dynamic RAM will remember it, but it will fade away. And as it fades away, you have to reread that byte of memory or that bit of memory in order to refresh it so it won't ever forget what it is. So the cycle for dynamic RAM is quite complicated. You constantly are reading the memory to refresh what's there so that if somebody comes along and needs it, it'll give them back, or comes along and needs it, it'll give them back the correct value. So very different technologies. This used to be expensive relative to this, but this used to come in more bits than this. None of that is true any longer. You can buy SRAM, and mostly you would buy SRAM because it's easier to maintain the bits for small projects. For large things, dynamic RAM still has a place. Now, we also can subdivide these into other types of things. Like we can take either of the types, usually SRAM, and we can call it video RAM. That's RAM which is specialized to have data which is going to be moved to your screen. Generally, it is what we call dual ported. And all dual ported means is two people can access the same memory. Usually one is writing and one is reading. And very much like synchronization we've talked about before in our multi-threading, the hardware will prevent somebody from reading bad data while it's being written. So the data gets written prior to it being able to be read. But it's primarily used for things like video RAM, read and write memory. Now you could use that also as a way to get at a disk drive or something like that, but we're not talking about that right now. We're simply talking at just pure memory as you might see it on a computer. Now, a more interesting category for us, oops, I got the wrong place. Well, called read-only memory. Read-only memory Basically does exactly what it promises. Whatever is inside of it cannot be changed. Now you'll say, when can it be changed? And of course, obviously, when you initially build it, it's going to have the wrong data inside of it. So there has to be some way for it to be changed. Well, read-only memory is not really practical anymore, but when it was as practical as it could be, generally what you would do is you would order it from the factory. And the people that made the memory would put the data inside of it for you, never to be changed. So when you got it, you would be able to use it to read the data that was in it. But if you needed to have it changed, you would have to reorder it from the factory as a different version. Could get quite expensive. Now it turns out that we also could build, after this, programmable read-only memory. Does exactly what we think it should do, is it allows us to reprogram the memory. And if we could afford the equipment to do so, we could program the equipment at the company that has bought the memory as opposed to the one that makes the memory. Now, normally, all this really meant was you didn't need to waste a chip in order to be able to program it. Rather, through some process, you could erase the chip and then program it a second time. The main category in the day of this was something called EEPROM. An erasable programmable read-only memory didn't really involve too much high expensive equipment. Rather, it simply involved that you have an ultraviolet eraser. The chips typically had a little tiny circular window about less than 1/4 of an inch in the center of the chip, over which there was a metal piece of tape or metallic tape. Normally, you would keep that little window covered, but if you needed to erase it, you'd remove the tape, and then you'd put the device that you're going to erase into a device that could shine ultraviolet light on it at the correct frequency. After a certain amount of time, you could take the chip out and the chip would have been erased, and you could then reprogram it with an expensive piece of equipment that allowed you to do the reprogramming. But it meant you didn't have to buy another chip. If the first one was bad, you could simply erase it and reuse it. Now, to become more practical, we'd like to use cheaper equipment, and we'd like to move it out closer to the programmer. So EEPROM was developed. I think I've spelled erasable 3 or 4 ways already. So it's electrically erasable. Basically what that means is you would apply a high voltage to one of the pins. And then you would use a protocol that the chip needed to know about, that you would be able to then go in and erase certain parts of the chip or even the whole thing, and then reprogram it right at your own desk as long as you had the light to be able to erase it. And companies sometimes would only have one of those that everybody shared. And then you'd have some sort of device to do the electrical programming. We still use this today. However, the programmer part of it may be something as simple as a USB connection to your host computer. So we've made a very slick way of doing this type of programming. And it's still usable by a developer or a programmer at his desk when he's testing a chip. He can erase it and he can reprogram it, put it back in the circuit, and test to see that it truly works. Now, one example of electrically erasable programmable memory, although we're not going to go through all the families, because this is a very common one these days, is flash memory. The flash memory is a form of EEPROM. We'll see on our ATmega 328P chip when we work on it that it has EEPROM, which is basically based on the EEPROM, just simply normal electrically erasable type of technology, as well as some additional flash EEPROM into which we'll actually store our programs. So it'll have two different types of EEPROM on it. It'll also have some RAM that we can use, in particular SRAM. But we'll come back to that when we get a little closer to having to use it. Now, programmable memory like this gave people ideas at the time of why don't we put functions in a chip and be able to supply those as things you could buy. And we know that can be done because the whole TTL family we talked about is an example of doing exactly that type of thing. In this case, it was transistor logic. And we could build multiple sized technologies. The technologies included LSI, MSI, actually, let me start with go in order here. SSI, MSI, LSI, VLSI. They stood for small scale. I'll just put the small. Well, I put first. I'll put the whole thing. Integration. This is medium scale integration, large scale, and very large scale. Very large scale integration. And they basically were based on how many transistors there were in a particular gate. So it was typical that small scale integration usually had between about 1 and 10 transistors. Medium scale integration probably had somewhere like between 10 and I'd say about 500 transistors. Large scale integration would be from about 500 up to about 20,000 transistors. And large scale would be 20,000 transistors up to probably about 1 million for the very large scale. And then their size is bigger than that. This is kind of the old nomenclature that was used in back about the 1980s when TTL was very popular. Because you could also scale these instead of in terms of transistors, you could scale them in terms of the number of gates that could be handled. So for example, something like an AND or an OR gate doesn't need many gates because each one is a gate itself. So in a NAND gate, there's 4 gates. But something like a flip-flop is probably medium scale because it's going to need, a couple gates per flip-flop, and each of those are made out of some number of transistors. So the various families look like this. Now, just out of curiosity, I looked for FPGAs are one of the size chips that we're going to talk about. They're called field programmable gate arrays, and not Gatorade like somebody told me one time. And in when was this? Back in 1919, one of the biggest FPGAs had 43.3 billion transistors on it. So the size is a little bigger than this, scaled up a little bit. Imagine what you could do with that many transistors. You could design a CPU. You could design all sorts of things. And we'll talk about the difference between that technology and one of the others that's more likely to be used for CPUs. But you'll see why we probably would develop them on an FPGA as a motivating reason as well. So that kind of covers what we would talk about as being introductory fixed base systems. Now, an FPGA is programmable, but these guys typically aren't. They do some function or set of functions, and that's what you get. What if you wanted to be able to program the function in? What if you basically just wanted to have some pool of transistors that you could arrange in various ways, and then you'd be able to make chips do what you wanted it to do? Well, they kind of fall in the next set of things we want to talk about. And we're going to call those things devices which are programmable logic devices, PLDs. Now, they're bigger than the complex logic devices, but they additionally bring along the ability to be programmable. Now, the first type I'd like to talk about, I have some slides that you can download and kind of follow along with me. So from the website, I think the name of the file is hdl.zip. Let me try that out and see if that works. And indeed it does. So use that name right there and download those and unzip them. And then I'm going to go through them. I'm probably not going to go through them in the order you see them in the file, but as long as you find it and open the one that I'm looking at, we'll be able to talk about them. So take a couple seconds to get that and give me a green light once you've got it. I saw 3 of you already had gotten it. Okay. So the first one is this set I want to talk about. Is something called a PLA. Which is a programmable logic array. Actually, that's not the first one I want to talk about. I want to talk about a PAL before I talk about that one. First one we want to talk about are programmable array logic. And it's just simpler if we go in this order. So here's an example of some programmable array logic. And it's just a little tiny chunk out of it. Now, there's a couple of devices. Well, on this particular one, there's a device that you haven't seen before, which are these guys right here. This is an AND gate that happens to have, coming into it, as many inputs as there are lines that it crosses. And it crosses 6 lines, so that's a 6-input AND gate. Same thing, same thing, same thing. 2 of these AND gates are fed to an OR gate. These 2 AND gates are fed to another OR gate. Now, when you initially get this, the X's are not here. Nothing is hooked up. Then you put it in your programmer device, and you run the programmer device, and you make a connection everywhere there is an X. Now, there are multiple versions of these. Sometimes instead of a connection, initially everything's connected and you break the circuit. We're going to pretend positive logic that we make the circuit. So what we're doing here is we're hooking this wire to any AND gate that would be on this, which is only this guy. This guy is hooked to him. This guy is hooked to him. So what we have coming into this is the fundamental product of X3, X2, not X0, which would turn this AND gate on if those three were all ones. Well, not quite. If they're all ones, this gives you a 1 here, this gives you a 1 here, but this would give you a 0. So we need, because we're on the inverted side of this to be a 0. So 1, 1, 0 turns this on. 0, 1, 1 turns this one on. 0, 0. Notice the last guy is not connected at all, so he's not part of the fundamental product. He's as though we Karnow mapped him away. These two guys, they're inverted forms, not A3, not A2, or X2, turn this gate on. And the positive versions of each of the signals turn this gate on. So we can program these gates just like we were building any type of logic circuit, any combinational logic. And the output of these two can be routed to that OR gate. The output of these two can be routed to that OR gate. So we could say the function of this is equal to that or that. The function here is equal to that or that. This is noted for the fact that we can program what's called the AND plane, but the AND gates are tied to fixed OR gates. This is specifically called a programmable array logic section. And through technology changes, these also are available as something called a GAL, which is a generic array logic. But they're exactly the same thing, except for how they're made. There's just slightly different technology, but they behave exactly the same. So a PAL and a GAL are the same thing. They're noted for the fact that we can program the AND plane. Now when we get to programmable logic arrays, we add to it the ability to also program the OR plane. So we can program both the AND and the OR plane. So we can take a min term, program it to an AND, many as we want. Then we can say this AND is connected to both of the OR gates. This AND is connected to this OR gate only. He's connected to the same OR gate, but also the other. And the last guy is only to the right OR gate, giving us more flexibility so we could actually define multiple truth tables inside of this particular function, because this is a fundamental product being ANDed together. It's already obviously Karnow reduced because one of the terms has gone away. Same thing here, a term has gone away. But notice this guy, this min term, contributes to two separate answers, whereas this guy only contributes to the first one, like this guy only contributes to the second one. He, of course, contributes to either one of the answers. So it's a little more flexible, technology-wise, a little more advanced, a little more expensive chip, although these are not very expensive chips anyway. But now if we have something, we don't have to build it out of multiple chips. We can program it inside of a single chip. That's kind of cool because we could become a hardware programmer. We're literally programming the hardware, telling it how we want it to behave. And that, of course, is a very, very important thing to carry on, because that modern programming of hardware is why we can do many of the things we can do. Now, once we've done that, it might occur to you that there really doesn't seem to be any way to program this thing. And do these only have 4 AND gates and 2 OR gates? Well, let's take a look at one in the wild. Here's some programmable array logic. Notice it's just a small chip. It's got, this particular one has 20 pins. It's not a very big chip. 1 to 10 down one side, 11 to 20 back up the other side. VCC on the top right, ground on the bottom left. Very much like TTL, and it's compatible with it normally. It's a PAL chip. And it has a diagram inside here which tells us how it's hooked up internally. And here it is. Okay. So our game plan here is to come into the AND plane, which is the stuff over here. And in our case, we're going to mark them as connecting, but what we're really doing on this particular chip is blowing the circuits. But what we're going to try to do is we're going to use the AND gates that are over here, which happen to be connected where necessary, simply to an output. And we're going to talk about what we're doing. In this case, notice that this has a single OR gate, single, so that when we've done this, we've picked that each set of AND can go to its own OR. That's very much like the original PAL program. Remember, when we were looking at this, we said, what's in the AND? The AND gates, each one goes to its OR. Well, we've got several now. Instead of 2, we have more than that. How many do we actually have going to the OR gate? Well, I'm going to blow this up. And we'll look at the top one here. There's 1, 2, 3, 4, 5, 6, 7 OR gate or AND gates, all being ORed together. And that's the same in all of the output stages here. We have one extra one. We'll talk about it in a second. But what is this device here? Raise your hand if you know what that device is. Miguel, what do you think that is?
Is that an inverter?
That's part of it. Yes, it is. Scott, what do you think? What else can we say about it?
It's a tri-state inverter.
That's exactly right. Because of the third line, we can turn the output to a Z by not enabling that line. Well, actually, it depends if we consider 0 to be the end or the out of the thing. But this guy is going to be controlling whether or not the output can be a 0, a 1, or a Z. Now, the reason for that is not so noticeable on this particular gate, but if you look at the next one, the next gate is capable of being either input or output. When it's input, it follows that path right there. Comes in, does not go backwards to that, so it takes a turn and comes over here and re-enters the matrix. So we take the blue pill. Now, if this is enabled, this is an output. If this is a Z, then it's an input and data can be passed in. Now, what in the heck do you think that interesting looking device is? You might want to take a stab at it. Robert, what do you think that is?
This is just a complete left field, but is it something that takes that and basically turns it into 2 buses, the input and not input?
That's exactly right. It's both an inverter and a buffer at the same time. So the data coming in gets split. Part of it stays the same. And then the other half of it, or I shouldn't say the other half, but the signal now also comes out. So if it's a 1 over here, it'll come out on the top line as a 1, on the bottom line as a 0. Now, if this is a Z, then the data will not be fed back. Now, there are ways we can later on feed back our own output, but not on this chip easily. These guys are AND gates. How many input AND gates are they? Are they 2, 3, 4, 5? How many inputs do they have? It looks like only one line there. Mikhail?
Is it 32? Because
Yes, sir. Yes, sir. That's exactly the right answer. Each of those AND gates have 32 inputs. Now, don't want to be Karnowing those. That's where Quinn McCluskey comes in handy, because we can then express our problem and reduce it down to only the inputs we need. But it could be potentially a problem with 32 inputs. That's a big number if you take 2 to the 32nd. I wouldn't even make students memorize that number. 2 to the 16, yeah, but not 2 to the 32. That's huge. So this is the way one of these chips actually looks for real. Now you'll notice this extra line coming across feeding this line here. If we go to the other side of the chip, what we see is that line is actually input over here on the other side. So it is really the input, but it's an input that's kind of isolated away from the pin itself. It doesn't get in the way of the pin. Notice all the others have a dot here. This line is exclusively an input. This line is exclusively an output. This line can do either, depending on how you program it. Now, each of the lines that are hooked to the AND gate can potentially be hooked to any of the lines coming down. Now, who's hooked to the line coming down? Well, you have to go find the dots. So pin 18 is hooked, but if we follow the line, well, we're going to see it's hooked to every one of the 32. No dots because we haven't programmed it. However, this guy coming into the matrix, pin 1, is hooked to this and that line, which are downward in the matrix. This is not 0, 1, so it's 2 and 3. That means everybody in the matrix can hook up to that pin by simply making a connection to those two lines. So the inputs coming in only hook where the dots are. Anybody crossing those dots, meaning on those two lines, would be programmed to be connected to those two dots. Now, this is one way they can be configured. A second way is we can configure them so some number of the output pins, input-output pins, or just pure, well, this one has an input-output there, can become flip-flops, generally D flip-flops, where the D is controlled by one of the OR gates, controlled by some number of the AND gates. In this case, where they're flip-flops, we don't need the extra line to control the output tri-state buffer, so we can feed it into the AND or the OR gate, so we can have 8 ANDs feeding it now. Each of the 8 has 32 inputs. But we can configure this to go through a gate. The gate itself, all 4 gates are equally combined by a pin 11. So for those, the output enable, which turns on the tri-statedness, is on pin 11. All the others have their individual, anything that's not a flip-flop can turn on their inputs and outputs at will. But the flip-flops are tied together. The other thing is the clock. The clock has to be driven from somewhere. And the clock, which is this input line here, is controlled by pin 1 on any chip that has flip-flops, which means the top guy here gets back his input. And this one has a 4 flip-flops, This one has 6 flip-flops, and this one has 8 flip-flops and no regular input outputs. So you can kind of buy them in the flavor you need for your problem. Notice here also it says I equals 0. There are some extra fuses, which it mentions. I don't guess it gives you the numbers here, but it gives you in the data sheet, where if we set the fuse from 0 to 1, this kind of output of the flip-flop is going to, oh, I'm sorry, I call this clock. This is not a clock. This is actually going to be used for clearing the chip. The clocks are all on this side controlled by pin 1. The clearing is controlled by, or reflected in the matrix. But they can have their basic outputs reversed. So while this shows Q here, the reason it shows Q is because internally it's hooked to not Q. But if we wanted it hooked to not Q, then we would have to program a fuse somewhere that says we want all our flip-flops to have their sex reversed. And again, we're talking always about positive logic because we could conceivably reverse our thinking if we needed something special. We wouldn't do that, but you could. So this is a very, very common popular chip. You'll still find these used in electronic hardware today, but not the high-end stuff. Even in the day of this, we could expand on this and make it a little better. To do that, we could get this generic array logic chip called the 22V10. The V has some meaning, and the V primarily means, unlike the last one, where we had the same number of AND gates feeding the OR gates, this one is going to have a variable number. So things that need a lot of AND gates can have them, and things that don't need as many can have fewer, which means our biggest number of AND gates can be bigger than we would have been able to have otherwise. So this guy, when we look at him internally, very similar, but he has on the outputs these logic blocks, which themselves are programmable. But if we look here, we'll notice that this guy has 8 AND gates feeding the block. This one has 10, this one has 12, this one has 14. The center two on the chip each have 16 AND gates. That's a lot of stuff feeding this gate. So you can have very complex problems as long as we put them in the right gates. And then it starts counting down again. Now these blocks, the OLMCs, will allow you to program the output so that it's an output, so that it's an input, just plain combinational, or so that it acts as a flip-flop. And we can look at that a little further down in the data sheet. Should have written down the page number. Where is it? It's got to be here. Did I miss it? Did I jump over it? I think I jumped over it. There we go. Here's our OR gate that we are coming into, right? We said we're coming into the block. So in all cases, we come into an OR gate. Then the OR gate can be either routed to the D of the flip-flop, or it can be routed so that it bypasses the flip-flop and has a output enable pin. Notice that we can program either active, or we can, active low or active high, where we go through an inverted tri-state buffer or a non-inverted tri-state buffer, meaning it can have low logic, meaning low is true, or high logic, meaning 1 is true. And we can do the opposites of that, high and low logic, in the case of just simply taking the data straight through without it being registered in a flip-flop. Here's some fuse numbers down here that tell you how you have to program them for a particular flip-flop in order to put them in that state. So these are called output logic macro cell configurations. The macro cell is this whole thing, and they don't really show you a picture. You can kind of see the picture because if you think about this OR gate goes either to D or poof, we just made it change this into this gate right here. We basically remove that. It's the same as going around it to connect it. And if we go around it, we don't need to see it. We also, though, have the feedback from the flip-flop going back into the matrix. So the flip-flop, the D we set, can also be data that we're going to be looking at. Notice in this case, we can't program it as input, but when it's this way, it can be either output or it can be input. So we get the best of all worlds if we use a device like this. This one, however, is still programmable array logic. I didn't show you the same versions for programmable logic arrays just because they're a little too much grid to see. But this one, it's not really hard to think about, but the real problem then becomes, how would we go about programming this? Are you going to sit down and write down what fuse numbers? They give us all the fuse numbers right here across the top. Here's fuse 1, fuse 4, fuse 40. The next line, you take that number and add it to whatever's over here. So we'd add the 1,452, a 16, if we wanted to have that fuse turned on. And it's got lots of fuses down here. We're at 5,764 plus, whatever the 32 over here. So quite honestly, I don't want to do that. I want to use a programming language. So to program these, what we're going to use is something called a hardware description language, HDL. And a hardware description language is basically, we're going to give the program kind of some information about which device we're going to program. And for most devices that it would be configured to use, it would already know the details of that device. We're then going to give it in a higher level language, a description of what we want the problem to be that we solve. It will then internally generate the bits and fuses necessary to be loaded onto the chip in order to be able to program it. And so we will talk at a higher level. Now, of course, you need to know, what if you were the guy writing the high HDL, how would you know how to turn the stuff into those bits? Well, you'd have to take from me a compiler class. I'm not going to teach you that in here. But such classes exist, and knowing at least that it has to be done is a good leg up on understanding how you might have to do that. I'm going to talk about 3 very old languages because the technology of PALs and PLDs, specifically for the devices we've talked about, really is kind of hard to find these days. It has been replaced with, I won't say better, but bigger and more capable chips. So what we're going to talk about will be the 4 programming language, or 3 programming languages that you might encounter. The one that's kind of closest to assembly language is called PALASM, P-A-L-A-S-M. And let's kind of take a look at that. We would, first of all, on our first line, state the device we're getting ready to use. And then for documentation purposes, we state that it's a PAL, and then a comment over here to kind of describe what's going on. More comment, which says, what is it that we're emulating? We're trying to emulate a CNT4S Charlie counter device. is basically a 4-bit counter. Well, they even say that in the thing. 4-bit counter with a synchronous clear. Synchronous meaning not timed with the clock. Oh, no, I'm sorry. Synchronous means timed with the clock. And it was written, this piece of code was written by Michael Holley and Dave Pellerin, I forget how he said his name. Now what we need to do is assign functions to the pins on the chip. We're going to assign a clock and a clear, some pins that are not connected, and a ground. Then on the other side of the chip, output enable, a couple not connected, and then 4 flip-flop outputs, which are inverted. The slash means invert here. 2 more not connected, and then VCC. VCC and ground are known words. Clock is a known word, but could be called anything depending on how you use it. Output, enable, and clear are also known words, as is not connected. Anything with a Q on it is assumed to be a flip-flop output. This is pin 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is pin 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And the compiler we're going to pass this to, the PALASM, which really an assembler, is going to know what to do with that. Now we're simply going to state how Q3 gets set, how Q2 gets set. What is the function for Q1? What is the function for Q0? So Q3 is assigned clear, not being asserted, or 0, 0, 0, 0, or those two, or those two, or those two. Actually, I said not asserted. In our case, it's positive, so it's asserted. So this is a counter. Remember that. So it's saying if we're counting, when should Q3 be turned on? And the cases they picked at are when clear is turned on, when everything is a 0, when these are 1s, when those are 1s, when these are 1s. Now, same type of equation, same type of equation, same type of equation. Now we have to remember that the sex of these has been changed because the name of the pin is already in the inverted signal. So we're not hooking to Q, we're hooking to not Q on the chip. So we could go through and build the truth table for it. And what we would do is we'd program the chip. Now, most programmers, when I say programmer here, it's being run by the programmer who wrote the program. But that program or device, after it programs it, is capable of checking to see that if you did the program right. And so what you do is you build a test bed. A test bed might be, as in this case, a function table. So here's a function table, which says if output enable is low and clear are these values, every time we see the clock, what should the outputs be? And if we look at them, 0, 1, if we're counting, remember this is written high bit, low bit, so this is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, and then 0, 0, 0, 0. And what we have here is he checks to see if clear is asserted, do we get all lows? And we give it a clock. If low is asserted to not be cleared and we see a clock, is this the value we see? And so forth. We could write all the possibilities and then we check one more time at the end to see the clear works, whatever the value is if we clear it. The programming device, if you tell it to run the programming code, will load this and check it by really running these signals on the device and looking at the outputs and give you a report of whether it worked or not. So the programmer input, what's described the chip, it knows what the chip is, so it knows how many pins there are. So we write out what each pin is attached to, write the logic telling it how to do what we need it to do, and then a way to check the output if the device can check it. That's the way PAL-ASM looks. It takes about 30 minutes to write a program for a device like this once you understand the constructs. If you feel like you could actually do that, give me a green circle. Some people go running and screaming out of the room because they simply do not want to write for hardware. PAL-ASM was always my favorite when I was writing for PALs because it lets you really, really say what you wanted the device to do. Another language of the time, and you can still get these and use them, but variations of them are much better to use. Here's another language. This one is called ABEL, A-B-E-L. And to be honest with you, I have forgotten what ABEL stands for. I mean, I think I'm looking at PAL-ASM still. Yeah, this looks more like it. Okay, we say that we have a module which we've named SN74162 because we're going to emulate one. -R3 is some option that the programmer needs. Be honest with you, don't remember what it means. The title of this particular thing is the title of whatever this is. They're emulating a Texas instrument. That's what SN stands for. 74162, that was a popular counter in its day. So Michael Holley here on the 30th of January in 1989 is going to build a synchronous 4-bit decade counter. Decade counter means it goes from 0 to 9, has 10 counts, decade. And it has what's called look-ahead carry, meaning it's non-synchronous. So the device, this was the module name, this is the device name, happened to be the same. You could have multiple modules. And well, you could have multiple devices in a module if you chose to, because one single chip can emulate multiple devices. It's going to be the P22V10 that I showed you. This is the one with the variable number of ands going into the ORs. Here are the pins, and here's how you'd specify it on this particular device. They're in order from pin 1 to pin 19, but you need to tell it that, because notice we don't use some of the pins. Clock, load, clear, enable P, enable T, data A, B, C, and D, QA, QB, QC, QD, and a carry. We know the datas are probably the data in for the flip-flops. We know the Qs are the outputs for the flip-flops. Matter of fact, down here, we've specified specifically that the Qs are of type D register with positive logic, and the register's name is going to be the feedback register when we talk about it as a whole. And carry is going to be positive logic. And it's this is a little complicated to describe without spending more time on it. But what it's basically trying to tell us is that it's complementary logic, meaning it's got a bar over it on the diagram, but we're using positive logic with it, so it's not doubly negative. And of course, now we're going to talk about grouping these together. Count groups together as a D register. The count is here, QD through QA. We already said it's a D register. And its data pins grouped together as a group will be called data. So we have count and data. Now we have 3 signal levels. We have a clock signal level, which is an edge. We have an H and we have an L. And we've described them over here as being describable as a C, a 1, and a 0. So it really just basically told, and this has dots around it to indicate edges. But the H and the L here, this makes convenience for writing our code. Now the enable signal is equal to both enable P and enable T being high. If either one is low, then we're not enabled. And the reason for them having two signals is one of them is faster than the other. And so you might choose to use it when starting up the chip or when powering it off or something like that. The next time you turn it on, you might want to use the fast logic rather than the slower logic, because the slower logic has other advantages, but right after power up, you're trying to get running as soon as possible. Now, notice we express our equations a little bit differently. We're going to assign to count, and notice it knows how to do some arithmetic for us. This is a little more high level. It also can test to see if this is less than 9. So count is going to be equal to, one of our terms is going to be count plus 1, ANDed with clear, ANDed with load, added with this computed enable signal, and count being less than 9. Or, notice that the ands and ors here are a little different looking. The or looks different. I believe it does. I don't remember right now the other one. Count and clear and load, but not enable, or data and clear and not load. All of those cause count to be bumped. And we know that if count is equal 9 and it's enable T, carry is supposed to be set. So we're not going to work through the logic and try to understand every line here. Just appreciate the fact this is much more algebraic, more expressive. It's not so much looking like a Boolean expression, even though it is. It has some extra things in it that the programmer can work. Why specify all these cases when we can just simply let it bump the count for us? Particularly something like this, where you'd have to specify 9 cases, or actually 8 cases. Well, 9 because the zero is there also. Finally, once we've programmed our device, we have some test vectors. We can test that if the pins are set to this, notice we use that C to mean a clock edge, count and carry have these values. And again, we don't specify it in binary. We take and use hex values for it. And we can give it a good testing. Different values of load, different values of low enable and enable P. Notice sometimes with both, sometimes with both, either one or the other. Load asserted, a case where load was not asserted to verify that 7 stayed in it. So writing a test is sometimes as hard as writing the program, because you want to really validate that what you said happened. Actually, literally, the hardware does that. But when you're done, you have built this chip. Now, would you ever need to build it? Well, we could go out and buy it. But we might also want to build a module which we name something else that contains 3 of these. And we could repeat this logic for multiple devices inside of our device, or various other things we might do at a higher level. So again, this would be fun to program in. It's very expressive if you understand the hardware you're programming. We can go a little bit more away from the chip's definition. This is actually continued. It's not one thing on one line. It's 2 lines, or 2 columns. This is the logic for a turnstile. Name is turnstile. Didn't give it a part number yet. Was done in 2001 in June. We don't know because it could be European. Revision 1. Designer was a guy named Guam. Company was EECE 143. We don't know what assembly or location was being used, but we know the device is a G16VH. So that was the GAL version we looked at. The one here has 16 pins, 8 of which are the flip-flop outputs. So it's a subway turnstile. And then we could list some allowable device types, but since we had already specified one, we didn't need to here. So what are our inputs? Well, here they are. Pin 1 is a clock. Pin 2 indicates we're in the state walkthrough. Pin 3 indicates we're in the state of coin. Pin 11 says the system is not enabled. Do we have any more below that? No, we don't. And then we have outputs where pin 14 is a pulse on the counter and 15 indicates locked. That controls the lock. We don't have any declarations or intermediate variables, but we could. So now we're going to describe and couple. And again, I once again forgot the name. It's been so long. I bet PU or PL stands for programming language. We define a variable word called locked, which stands for bit of 0. One called open to stand for a bit of 0. So we build a state machine. A little different than ours because it's mostly expressed as a language, not the internals. But the sequence called lock, if the present state is locked, to move out of that state, if we have a coin, the next state is open. If we don't have a coin, the next stage remains locked. So we're going to spin in here, waiting for a coin. When we get a coin, we're going to transition to the open state, where we're going to wait until we see walkthrough, meaning the guy has hit the sensor for walkthrough. If he hits the sensor, the next state we go to is locked, where we're going to wait for a coin. Otherwise, the default state is to just stay here forever if we didn't see that. And we're going to output a pulse on count. Now, the pulse on count, as you can see, if the default is to go to open, but we don't go to open, we're going to stay here counting the number of times we waited for a walkthrough. Now, we could have added other things to that. And there was an old processor that used this language, actually, and this was a little bit broken. We'll pretend like it's 100% correct. Notice that we don't have any test logic here. We could build a test bed, but the machine this one was being tested on only had the programmer part. It didn't have the test piece. So we would not feel that this is safe and sound and load it up and then rely on it until we found a machine to test it on. But to test it, we'd have to write a very thorough test to make sure there's no cases where somebody puts a coin in, doesn't walk through somehow, but somebody else can walk through. We don't care as long as it locks again, because it's just a different guy put the coin in. But if two guys could somehow get through, we have a problem, because I guarantee you it's not going to take very long for somebody to figure out how to do that. Okay, any questions about anything having to do with these with the hardware descriptor languages that we just talked about, or programmable logic devices in general? Robert?
So are we just kind of responsible for knowing what they are and that they exist, or are we going to get more in depth with them?
You may get more in depth, but for this test, remember, there's nothing on HDLs on it. Most of this is just so we have time to give you the material without me giving you the test on an inconvenient night. Okay. Let me close that. Okay, so We managed to get up to about 1 million transistors. If we got bigger than that, which we might, we actually change kind of the name. And what we do is we say CPLD, which are complex programmable logic devices. And the names become a little blurry above that. It kind of sits between the PLD and devices which are bigger, like FPGAs or ASICs, which we'll talk about in a few minutes. But it sits between them. And typically, they're characterized by having on-chip, non-volatile memory, meaning that I can program them and I can turn the power off, and when I turn the power back on, the program is still in them. Now, we actually talked about, although I forgot to mention it earlier, a type of memory where that's not true. Anybody remember what that would be? Mikhail?
Dynamic memory.
Yeah, that's one of the cases of it. We go way back here. RAM in general, particularly static RAM or dynamic RAM, loses its contents if it loses power, which is why very often you'll find these in a computer backed up with a coin cell, so they don't lose their memory when the computer is powered off, but otherwise they will. And in the case of FPGAs, we'll see they do also, but we haven't gotten there yet. In the case of this, non-volatile memory means if you turn a complex programmable device off and turn it back on, it's ready to go right away. Memory is still there. So that's a characterizing factor about it. They can use about 10 times what an LS, or in terms of transistors, hold about 10 times the number of transistors. So they're a little bigger scaled. The major vendors for these things these days, if you were going to be going out to buy one, is a company called Xilinx. And their particular thing is called Cool Runner. They have the Cool Runner brand or whatever within their thing. Another one is a company called Altera, and it's owned by Intel. And they have something called the Max series. So if you saw a device and somebody asked you, hey, it's a Max 341, be suspicious that it's an Altera chip, and it's probably a CPLD. There's other companies that make them, but they're the primary big ones that we'd see. Now, you can put small programs and small logic problems in here that are significantly bigger than what will go in a PLA, but they're significantly smaller than what will go into an FPGA. So for our purposes, unless we were building glue logic to support main functions, because we're kind of CPU based here, we need to talk about the differences between FPGAs and ASICs and what technologies we're talking about here. We're going to focus in on FPGAs, which are called field programmable gate arrays. Abbreviated FPGA, of course. And this is going to be our focus in terms of where we probably wind up with most of our questions and things. Again, major manufacturers, same bunch. Xilinx. Now, Xilinx in this has a series of families: the Vertex, EX, Kintex, the Artix, and the Spartan. And you'd have to look at their website to determine which is the most powerful. But it's like different series. It would be like the difference between different models of a CPU and the speed they can run. And even the Spartan might be more like a 486 than a 586 type of thing. The other company also, Altera / Intel. They have things like the Agilix, Stratix, the Aria, and the Cyclone. My favorites of these, by the way, just because of their price, are the Spartan and the Cyclone. They tend to be lower function, slower, but cheaper. And that'll make a difference. And then there's a couple other companies that make them. One you might see would be, I guess I'll tell you about this, Lattice Semiconductor. They also make some FPGAs. Now, key to these things is, and just like the SRAM and DRAM, they have volatile memory. They need to be programmed every time they are powered on. You might say, well, that's terrible. Well, not necessarily. One of the benefits that gives you is that because they can be programmed, you literally could change what they do while the machine's running. You just would make sure you didn't use any of the functions of that chip while you were doing it. But the technology is a little different. And one thing I want to mention about them is, compared to ASICs, they're expensive per unit. And we'll come back to that. However, they have what's called a reduced NRE because easy to reprogram. NRE is non-recurring engineering. It's basically the stuff that happens before you go into production with something. In the software world, we would call it writing the program. And you'll see why in a few minutes. The ability to reprogram them is a good thing. It's particularly good because they're expensive per unit. And if you were to have to make changes and had to buy new units, just like an old ROM, you'd be spending a lot per unit. Now, you can buy programs that are written to run in these various types of chips. When you do, oops, what you have is something called intellectual property. So I can pre-buy function. So they might have a really fancy fast adder subtractor. You can pay money and buy that and not have to program itself. Now you might say, why would you ever want to use one in the first place? I know a lot of you are thinking, he's given us a lot of facts, and when he asks me questions, my head's going to explode. Well, that'll happen to a couple of you, but hopefully not most of you. We might want to write intellectual property and sell it to other people. Maybe we have a function that we can do better than anybody else because that's our business. And we want to sell it to other chip makers. Maybe we have this great encryption scheme that we've invented. We could make intellectual property out of it and sell it to other people who then would have this very well tested, very good, strong IP. Intellectual property, by the way, is called IP. I didn't write that up here. I should have. Not UO or an equal sign. Don't get off the UO key hand. Okay, we'll use that IP instead. What happens when you get 2 of every key? Okay, so why? Here's a question. Let me write this way. Why would I use an FPGA? Why would I need one? Anybody want to take a shot? We know one use, and you can give me that one as the first one, is because if we write intellectual property, other people could use an FPGA to make use of it. So we could do the same. We could make uses of other people's expertise in a chip we design. Anybody else have any other ideas about what you might do? Robert?
You probably chain together multiple IPs to solve a larger problem in chunks.
Absolutely. That would be a good use. Okay, here's one we could do. How about we could implement a specialized programmable CPU on the FPGA. So let's say maybe we wanted to write a CPU that could work problems in parallel on separate CPUs. Well, we can kind of make it do that, but what if we needed to have 15 CPUs or 35 CPUs? Well, we could certainly write a program that represented the pieces of that code we needed, and we could make 15 copies of it. So we could build ourselves what we would call not general purpose CPUs. We mostly already have one in our computer. What do we have in our computer that's specialized to do one thing and do it really well, but it's not a CPU? What do you think, Scott?
Guess graphics cards.
Yeah, your graphics card. It's probably on an ASIC, but an ASIC and an FPGA, other than internally being different, really do the same things. They function the same, but absolutely, it's not general purpose. Can we program it? Absolutely. Could we build one that we couldn't program? Absolutely. The old fixed pipeline graphics card in early computers. You couldn't program it, but it was a separate card. In some of the original CPUs, the floating point processor was on its own CPU card, which wasn't really a general purpose CPU. So we might want to be able to do that. We might want to have something we could do, let's say cryptographics. Maybe we want to be able to encrypt streams of data. Maybe we want to be able to do 50 of them at the same time. We could build that into an FPGA, do the same algorithm in parallel on the same chip. A lot of opportunity. We could make something that could run a real-time operating system, an RTOS. We could make our CPU that we would develop as an RTOS be able to be deterministic. I spelled that wrong, but you know what it means, which is basically guaranteed worst-case timing. So we could write code which would guarantee that our user would be able to complete an operation. We might also be able to run Linux on it, maybe. Intel has a piece of property, which is an example of this, which is Intel, they call it NIOS 2. It's an operating system, which is kind of a real-time operating system because it is deterministic, and it'll work. Xilinx says one is well to compete. I think they call it microblaze. It's called the microblaze soft processor core. What that means is, to a program that you write, not on the FPGA, but be given as the FPGA as data later, that would be the program. Now, the chip itself has a program on it which runs as though it were a processor. The processor could be designed any way your little heart could design it. Could be any, it could look like Linux, it could look like an RTOS, it could look like Windows if you wanted it to. And there are two companies out there that already supply intellectual property. So I could imagine, you know, I need a problem run and I need it to be run in parallel. I might buy 15 copies of this, put them on a chip in parallel. Now I have one chip to which I can supply a program. What program? Well, the program could be any program I could write, and I would have a compiler somewhere which could turn it into the assembly language, which could run on an Intel NIOS processor. A lot of opportunity here. Basically, we can write hardware that can do most anything. There also, you will see this, which is a little becoming popular, called an SoC. Stands for System on a Chip. This is kind of an FPGA to which they have added a lot of extra function, but the entire operating system and everything has been boiled down to be a single chip and may also have analog features built in. So I'll just leave that as modern technology that I'm not going to show you, but just be aware that it's potentially something out there that you might see later. Now, let's sidetrack for a second here, and let's talk about ASICs. An application-specific integrated circuit. Now, they have a huge NRA. But in the wrong window. Low cost per unit. They may be bigger than an FPGA. Now, I don't mean necessarily only in size. They might have lots more transistors. They do have a different internal structure than an FPGA. Now, you'd be using them for all the motivations you had to use a to use an FPGA, but in this case, they are non-volatile. You go, well, why don't I use those all the time? And the reason is because of this. And the NRE is, the development time is approximately the same, but here is the real issue with it. On an FPGA, I write a program. Okay, where did I put these? I must have written them on there somewhere. Nope. Oh, here we go. I write a program. Now, each unit is fairly expensive. Now, not as much as an ASIC, but fairly expensive. But when I write my program, I make a mistake and have to go back and program it again. These are reprogrammable. So as a programmer at my desk, I can reprogram the same device over and over and over again. So that reduces my NRE because I'm not having to buy a new chip every time I reprogram it. They're still expensive, so I don't want to buy 15 of them. But since I'm going to reuse them, every programmer can afford to have one, 10, 5, whatever number, and I can use them. So what I can do is I can develop the code that's going to be put on an ASIC, assuming it fits, which it will because it's an FPGA, or if it's going to be big in 2 FPGAs, where it'll ultimately wind up on 1 ASIC, get it working here, because it'll be relatively inexpensive to do that. Then once it all works, I'll bite the bullet once and buy a very, very expensive NRE. Well, I'll buy a cheap chip, but when I buy the chip, I have to have these programmed by the factory. I can't program them. So it's extremely expensive to program an ASIC, but it's really cheap once you get one programmed. So if you're going to sell 1 million of something, you're going to put it on an ASIC. It'll cost you a lot. You'll develop it on an FPGA, then you'll move it to an ASIC when you get it right, and then you'll sell millions of them at a very low cost per unit. You'll charge your users a lot more than your low cost, but you'll make a lot of money. If, however, you're only going to make 10 or 12 of these things or 100 of these things, you're probably going to do them and leave them on an FPGA, because the programmer then can just make updates to them when you need to. And even if you send them out, it's easy to get your users to make the updates if there's only a handful. We're going to focus on the FPGAs. And we're going to now start thinking about programming them. To program them, we're going to use, again, hardware description languages, HDLs. And we're going to pick from 2 in particular. The first one is a language called Verilog. Second one is one called VHDL. Now, upsides and downsides of these. Let me put them in my notes here on this hardware description language. We're trying to tell it, again, kind of like functional programming, we're describing what's to happen as opposed to all the details. We'll let the compiler figure that out for us. Verilog is primarily used in the US and taught in schools. VHDL is primarily used in Europe and Asia. Now the question becomes, if I had to teach you one of those, which one would I teach you? Well, let's take a downside of the first one. Downside of the first one is it's too much like C or Java or any of those languages. It picks up in programmers, software programmers, which most of you are, bad habits, because you'll start programming the hardware as though it were software. And you'll write a lot of bad code that way. Secondly, in this class, we don't have enough time to teach you the full language. So it would be better to teach you something that if you went out and got a job, you'd not likely be using. So in the US, you're not likely to have a place that uses VHDL. But if you did have, you would have seen it because Bastien showed it to us, and it would be no problem learning it. Now, if you just saw this and went in and saw Verilog, it'd be easy to learn. It'd be hard not to do this, but this would be very easy for you to do. Also, if you went on a job interview, everybody assumes you at the university they taught you Verilog. And by having VHDL in your tool belt, you have an edge over people that only know Verilog. And it would not take any of you very long to be able to pick up Verilog once you knew HTML or VHDL. Now, the only hardest part of VHDL is what the acronyms stand for. Well, it's an acronym with an acronym in it. It really stands for VHSIC.hdl. And you go, well, that helped. That stands for very high speed integrated circuit hardware description language. You could be really cool. Imagine if you're at a party somewhere and somebody says, well, I wonder who knows something in here. You could raise your hand and say, I know what VHDL stands for. And then you could spout that out. The people, I bet they'd be talking about you the next day. Okay, let's move ahead here. So VHDL tools. There's some mighty fine tools made by Xilinx. ZXI. Xilinx, something called the ISC Webpack design software. And some of their chips require that. It is deprecated. And ISE stands for Integrated Synthesis Environment. I didn't remember that one. They also make something called Vivado Design Suite. And it is the modern one for the more current FPGAs. But like the Spartans I told you earlier about, that sort of a chip, if Xilinx were doing it, it would be on the older version. And Intel competes with them. Something called Quartus Prime. I think they've been watching too many movies. Now, these can simulate non-existent hardware. So you're giving it hardware to execute, and it does simulation of it. Next, it can do synthesis. But once it's determined how it should behave, it can write code with the program that works with the device you want to put it on, or not. It'll either fit or not fit. We generally are writing thinking about behavioral programming. And this includes the fact that we are going to include, includes test benches. Test benches like those simulation tables we saw earlier. Sometimes we might program at what's called the register level. This is very low level. Actually called the register transfer level, which would be abbreviated RTL. We ourselves will probably program there because we'll learn the most by doing it. And it can be synthesized. Behavioral may or may not be synthesizable, but it can be able to be simulated. So I can write behavioral code that exists, non-existent code, but not only that, it can be non-existent, but can't even be used with existing hardware. That's how we come up with brand new things that we can't build, but we can test to conceive of whether we could build one. However, once we can get to the register transfer level, we can actually build one of those things and put it in a chip and test it. So register transfer level is a powerful way of doing that. There's another level we can work at, which we don't want to work at, which is called structural. I don't think I asked it to open the window, but what the heck. And this is where we actually work right at the hardware level. We're not only telling it what the registers are to do, we're telling it what all the bits that we never want to even talk about have to do. Now, a good system after it does this will do something called place and route. What place and route does is it figures out, now that it knows what the circuit should be doing, what pins everything should be hooked to, and internally, how to hook those pins together. Very, very difficult problem. Then we already mentioned the test bench. So what we really need, just for demo purposes, we need to be able to do a syntax check on the code we write. We never need to be able to do the analysis to make sure it really does something. And then we need to be doing what's called elaboration. That's kind of like running the compiler. This checks the syntax. This looks at the code to make sure it can be compiled. This compiles it. And then we would actually, after we had compiled it and elaborated it, be able to test it. So we could have our test bench run out here. I'm going to run some software which is called GHDL. And a second program called GTK Wave, for which I have a Windows installation that I'm not going to make you install on your machine because, quite honestly, we have about 30 minutes to talk about it, and it's in the megabytes download, plus it takes a while to get used to using it. So I think what we're going to do instead is I'll show you the code and possibly run you some examples of using it so you get a better idea of how it works. Okay. Now, if it will put you in tears, you can contact me after class sometime and I will give you a copy of it to use and to play around with. But, you know, if it doesn't move you to tears, it's just more software that you might accidentally try to use and break something with. So just if it'll bring you to tears, I'll give it to you. So let me, first of all, get my environment set up. Let me do it here. Hold on a second here. Where'd that window go? I've not mentioned it. OneDrive is a pain. Okay. Now this is mostly run, the software itself. See, I'm way down in some subdirectory here. It's run from a command prompt. Do a directory in this folder. What we'll see is a bunch of subdirectories. I have 2 programs installed, GHDL and GTK Wave. Have some notes about how to do certain things. And then there's one batch file, which sets up all the path. So if I say set and run that program, it's going to change my path so that it contains things that will let me execute the program. So what I'm going to do is I'm going to, let me look at my data again, CD into a directory called work and show you what I have in there. In here, I have some VHDL files, which run these functions. So for example, I have an OR with 2 inputs function. I have an AND with 2 inputs. I then also have a test bench, which will test to see that that program works. Now let's just, without looking at the code, let me actually show you the operation of this in case you ever need to do it yourself. First of all, I'm going to take the 2 input AND gate and we're going to test it. So I have to first of all compile it, but to do that, first of all, I need to check its syntax. So what I'm going to do is I'm going to say GHDL-S for check the syntax of AND_2.VHDL. Got no errors, so that's good. Second thing I said I had to do is I need to analyze it to make sure that it will compile. So I changed the S to an A. It compiled. I'm sorry, it passed the test. Now we need to elaborate it. When you elaborate it, you're elaborating, actually, let me show you that. I do GHDL-D for display. You'll see that it has created an entity and an architecture which say that I now have an entity called AND2, which is going to be executed by an architecture named Arch, which is one of the architectures of AND2. So it built that for me and got the structure ready, but now I need to take and do an elaborate. Since I'm elaborating the name that's in that displayed folder, I don't need the VHDL anymore. So I shall elaborate it. Now that I have elaborated it, I'm going to run it. To run it, I'm going to say GHDL. Actually, I can't run it yet. I've got to make the test bed. So I have to do the same things we just did. GHDL-syntax and to TB.VHDL, because it's the test bed this time. I want to analyze that. Get rid of the VHDL. And elaborate that. And while we're here, we'll just look to see that I have those on display. There they all are. Now, the way to think about this is AND2 testbed uses AND2. AND2 can't run by itself. It's just a chip. So AND2 testbed is a simulation that can use a chip. So now that we've done that, we need to run the testbed. So I'm going to say GHDL- -R for run, -- VCD equals, and I'm just going to say VCD.VCD. I'll explain that in a second. And that should be good enough. Oh, and then I need to make sure it had the name in it up front here. Before the VCD, I need to say AND_2_testbed. Now I'll run that. Ran successfully. Now, I can't see any output, so I'm going to run the GTK Wave program to look at the output. And it's going to use this VCD file in order to see what to do. Let me show you the inside of that. That's what's inside the VCD file. Okay, so that's the execution of the simulation. So we want to process that file. So I'm going to say GTK wave. And the name of the file was and to TV. And the piece I need is the dot. Actually, I call it VCD.VCD, didn't I? Make it easy on myself. Okay, so we'll run that. Splash screen comes up. This window comes up. Now, I unfortunately can't make the text any bigger, but what I have on the left-hand side is internally in the program, there are 3 registers, S1, S2, and S3. If I click up here on this thing, which is called A2, it'll show me that each register is named A, B, or Y. That sounds like Boolean names. So what I'm going to do is I'm going to drag A over here. I'm going to drag B over here. Drag Y over here. And what I have on the right is a timing diagram. It shows me when A changes, when B changes, and what happened to Y when I did it. I can visually check that to see if it does the function I need it to do. I'm going to zoom in, and the keys I push for that are Shift, Alt, F. And what it did is zoomed in to something that will hold all of the output. And the output has A and B being unknown, producing an unknown output. If A and B are 0, the output is 0. If A is a 0, B is a 1, the output is a 0. If A is a 1, B is a 0, the output is a 0. If A and B are both 1s, the output is a 1. So that's exactly the right answer. So we know that our AND to function works correctly. So let's take a look at the code. You know, this is a lot easier than you might think at first. Just like we might use imports or something or an include at the start of a program, we say we want to use the IEEE library. And out of that library, we want to use their standard logic 1164 package. And we might call any of the methods in it. This is like a star is used at the end of an import in Java. So we basically copy those 2 lines. Now inside the program, we have 2 blocks. We have an entity and we have an architecture. The entity, we give it a name and we say it is what follows and it ends right here. The architecture, we're going to call Arch. It's of this entity. And it is here and ends right there. Now, you can have multiple architectures for a particular entity, and we have ways externally to pick which architecture we're going to use. Normally, we have a configuration section if that's going to happen. For anything we would write or talk about, we will only have one entity and one architecture, so we don't need a configuration section. Now, just like we did in the other HDLs I showed you earlier, we describe what the inputs look like on our chip. This is a chip. We're making it out of an FPGA. We're going to use 3 pins. The first pin is an input pin. Its name is A, and it's going to be of the type standard logic. That means it's just a binary pin. B, same thing. We have 2 input pins. Y is 1 output pin, which we're going to call standard logic. Notice that semicolons inside of this port thing are separators. They're not terminators, meaning there is no semicolon after the last item. They only separate the items. This semicolon here, however, is a terminator. It ends the port. So once we've defined the port, we need to go to the architecture section and say, what do we want it to do? Well, the architecture begins here. What does it do? It assigns to Y whatever A and B are. And that's our function, so we know that does the right thing. We're done. That's all we needed to do to define a chip. But we have to build a test bed to be able to use it or to test it. Test bed is a little more complicated. We put this off to one side here. Test bed starts with the includes. Says we have an entity named and_2_test_bed. Notice, because it's a test bed or test bench, it doesn't have any entity. It does have an architecture, however. We're going to call the architecture test. It's going to be of this entity, and it is here. Well, what's here? Well, right here, we have a component we're going to use. What component are we going to use? This guy over here, and 2. What does his port look like? Well, his port, amazingly, we have to copy exactly what he has inside of him right here. So this program knows about his port in that component. Now we have the ability to use an and2 inside of our program. So how are we going to do that? Well, we're going to declare some signals, S1, S2, and S3 of type standard logic. Notice these aren't in or out. They're either one we want them to be. And we're going to create an instance of and2. The instance we're going to create, we're going to call A2. And we're going to do a port map. We're going to map its pins to our pins. So its A pin get mapped to our signal 1. Its B pin gets mapped to our signal 2. Its Y pin is mapped to our signal 3. Now what that means is whatever A is equal to, S1 will be equal to that. Whatever B is equal to, S2 will be equal to, and whatever Y is equal to, S3 will be equal to. So now we build the test process. We're going to call it test bench process or TV process. Here's the process itself. Let it begin here and end down here. And of course, the test ends down here. What are we going to do? First of all, we're going to set S1 and S2 to unknown. We're going to wait for a nanosecond. Then we're going to set S1 and S2 to zeros. Wait for a nanosecond. S1, S2 to 0 and 1. Wait. 1 and 0. Wait. 1 and 1. Wait. Then we'll do another wait. If we don't do this wait, it'll repeat. Processes run forever. And they run asynchronously to any other process that's running, meaning they don't care what the other process is doing. This is constantly running, because if you think about a chip, it doesn't know what any other pin is doing. It's going to just make a pin be read whenever the pin changes. We might synchronize it to a clock, but we might not. So this test describes exactly what we saw in the GTK wave program. So let's take a look at an AND4. And see what we'd have to do to make an AND4 work. First of all, let's look at the details of an AND4. You could almost tell me already how this works. Has the includes, has an AND4 as its entity's name. The architecture will be down here. Has a port. The port has 4 inputs. Has a Y for an output. Even I can figure that out. It's going to use a component. called an AND2. So it itself is going to make use of a different component, where A and B are the things that the component said it had. And we're going to have a couple signals. So let's see how we use it. Well, it looks like we're going to implement 3 AND2s to be the AND4. The first one maps A to A, B to B, and Y to S1. The second one is going to, this is C and D, it's going to map A to the C inside this AND2. This AND2's B will be mapped to the external D, and this guy's Y inside will be mapped to this S2 here. So this added up A and B, this added up C and D, so now we have to add up A, B, C, D. So we can take another AND2, we can take its A, get it from S1, we can take its B and get it from S2, we can take its Y and get it from the Y of this chip because it's where the ultimate answer is. That's the entire architecture. We simply made use of the 2 components to create a third component that we use to create the answer. So that's very simple. Nothing hard about that. Let's look at its test bench. Okay, the test bench doesn't know anything about the AND2s. It's only going to talk to the AND4. And the AND4 has a port that looks like this. It's going to have some internal signals it might want to use. And then we get to where the process is going to begin. Using the AND4, it's going to port map the AND4's A, B, C, and D to the 4 signals here. It's also going to map the Y to signal 5, because remember, in the other picture, this goes into A and B of the 2-input AND, this goes into C and D of the input AND, and this is where the output comes out of that last stage. So it should be the output of the AND4. Then we just build our test bench. We're going to go through every combination of inputs for a test 4. There's 16 of them. And we know at the bottom there'll be another wait, so we don't accidentally loop back. So let's compile and run this one. We don't need to do the AND4 or the AND2s again. They've already been compiled. Let me see, where do I go here? Well, I need the CD, the OneDrive. And I think I got VHDL next. Nope. Oh, I know what it is. It's desktop. I can't do this. Why am I getting capital letters and it's not pressed? Okay, now let me see if I can sort away that thing. And I have, because I started this again, I have to rerun the batch. Let's see. Nope, don't want that. There we go. Couldn't have closed that window down. Okay, so in here what we want to do is we want to check to make sure that we can compile and4.vhdl. So GHDL, first thing we need to do is check the syntax. We're checking we're checking and4.vhdl. What did I spell wrong? Is and_4. In GHDL, we want to do what second? We want to analyze, or do we want to do something else? We want to analyze. Then we need to elaborate. Elaboration doesn't need the VHDL. If we did a GHDL display, we'll see it's in there now. Now we need to do the test bed the same way. Okay, now we're ready to run a BTK wave. And does wave have an E on it? I forget. It does. We want to run and for test bed. We'll put our output in the, what is that, it's VCD equals, right? We'll just put it in the same file. Oops, I did something wrong. Oh, no, this is GHDL, isn't it? I'm running myself ahead here. There we go. Now we can use the GTK wave. And the GTK wave just simply uses that VCD.VCD file to do its thing. Okay. We could look at all our outputs and inputs and things, or we could look at the signals like we said, just the signals. Let's just look at the signals for now. Oops. And there's our signals brought into focus. So what we actually have is we have signal 1 and signal 2. These two guys ANDed together. These two guys ANDed together. So anytime the first two or the second two are ones, the out should be a 1, except we're ANDing them together. So that means only when all 4 of these are a 1 will we get a 1 in the bottom line. And in fact, we do. So that worked just beautifully. I didn't mean to close that. But that's okay, because what I'm going to show you now doesn't need to be run. Let's say that I was asked to write a T flip-flop. And you might be someday. How could we go about doing that? Well, obviously this is not the test bench. This is the real code. So let's look and see what we're going to do here, because this will give us a couple other things we haven't seen yet. I don't know why that semicolon's on that. Oh, it's probably a width thing. No, I just typed it on the wrong line. Headers entity T flip-flop is, here's a port. The port has a clock, a clear, a T input, a Q, and a Q bar. That sounds like a T flip-flop to me. The architecture for this, or the behavior. Now this is a little different. We're going to have the signal, we're going to call it Q hold. We're going to begin. Now, we're not inside a process right now. So when you see an arrow like this, it means create a process wrapper this entire statement with it, and make it do this Q equals Q hold constantly. So every time Q hold changes, I don't care what the clocks are doing or anything else, Q is going to change. It's a process. Here's another process. At the same time this is doing that, this process will run. And as a matter of fact, down at the bottom, I don't have a third one in this one, but if I had another process, it would be running at the same time as well. So the process is triggered here, but it only runs if clock or clear change. These are the activation variables, basically. They activate this process. If clock changes, process runs. If clock doesn't change, if clear changes, it runs. Then we're going to have inside that what we're going to do. What are we going to do? Well, if clear is equal to 1, we don't care what clock or anything else is doing. We make Q hold, remember that external variable, equal to a 0. Otherwise, if we have a rising edge of the clock, then if T is a 1, Q hold will be the opposite of what Q hold was. Otherwise, Q hold doesn't change. In the first if and the second if, in the process. Now, it turns out that because we use this type of a marking inside of a process, we don't get another process, but what we do get is this doesn't actually happen here. It happens at the end of the process. So the process ends and it goes back, and if clock or clear changes, it happens again. But this right here might have noticed that Q hold changed. If it does, it'll change Q, because remember, it's Q and Q bar that we want to have change anyway. Now, instantly, oh, this is outside the process. This other process is running at the same time. It notices Q hold change and it makes Q bar equal to not Q hold. So we wind up getting Q bar and Q set if the process managed to change Q hold. And yes, that takes a little thinking about. That's one you should read and take with you. Now, you don't have a copy of it right now, and I don't have a way to give it to you easily, but after we've had the test and everything, you might have a copy to look at. Here, let's take another look. How much harder do you think a D flip-flop would be? Well, if we look at the D flip-flop, this changed to a D. This changed to a D flip-flop, of course. We go in here, the only thing that really changes is what happens on the rising edge. Instead of it toggling, D passes through to Q hold passes through to Q hold. All this setting of the other stuff remain pretty much the same. So once we have a basic flip-flop, it's easy to generate them. And we could generate 100 of these inside of one chip. Or we could 5 of these and 16 of the T's and a few flip-flops that are JK type. So we're not going to go over the JK because we're too close to the end of class time. But you can imagine that the only real big changes are going to change when we set Q hold. And also, clear may do something slightly differently because it's going to be testing. Well, actually, clear won't, but in our port up here, instead of just having a D, we'll probably have a J and a K input. Now, what you need to do is kind of let this wash over you rather than worrying too much about the details of it, so that if we do some of this, and we'll probably do some of this as part of the microcontroller discussions, you'll be in a good position. If you want to download what I've downloaded here, and you think you paid enough attention that you really can't make a mess of it, because if you do, you just simply delete it all and reinstall it. The file you want to download to get a copy of what I've been working with, let me see, do I have Windows open anywhere? I do not. What am I doing? I think it's just called VHDL.zip. Let me look and see. And it's lowercase VHDL. So somebody throw that in the chat. I don't have any place to write it down. And you can download that to your desktop. Double click on it or whatever you do to unzip it to your desktop. Then using a Windows command prompt, you want to CD into it. Well, let me get myself, first of all, to my desktop. So you'll CD into VHDL lowercase after you've unzipped it. You may have to do that twice because you might get inside of there another directory called VHDL. If you do, just go to the one that contains the batch file. Then type the name of the batch file. You also can hit just SET and push the tab key, and it'll fill it in for you. Run that. Every time you would enter a new window, you have to run that, but then you don't have to run it again. And then you can CD from there into the work directory, and you can see all the files and things that we were working with tonight. There is a do it program in there you could type that runs everything and also compiles everything if you wanted to run that. So if I say do it, it compiles everything, it runs everything, and it runs all of the test benches. Notice that the test benches now have names instead of ecd.vcd, but you can figure that out. In the highest level where the above work here, if you haven't gone down to work yet, there is a file called notes.txt. Where'd it go? If you open notes.txt, which I don't know where it went.
Professor, you left the S off, that's why.
Oh, did I? You could look and see all your commands and just some details about documentation and things you might want to look at. Okay, everybody, at least now if you're running Macintosh or you're running Linux people should know what to do. I mean, these are programs you'd run all the time over there. But if you're running Mac, you're going to need to rewrite that batch file to be a simple script that simply sets your path for you. That's a piece of cake. Okay, any questions? So I'll be here tomorrow night if anybody wants to join me. And I'm going to be studying away. And then you all have your exam at 6 o'clock on Monday evening, assuming everything works. Now, if the internet is not working or something that night, check your email. I might have given you instructions. If not, send me an email, tell me you don't have the internet. And unfortunately, the makeup test for this is hard. And so I avoid giving it, but not much I can do about it. I can't give the same test I give to the class because too many people would know about it. So if you're a one-up, can't get on the computer, you'll wind up taking the makeup, and that's unfortunate. But if for some reason we're down and it's published that it's down, double check your email first of all to see that I didn't send you instructions. But we would just put it on Wednesday instead of Monday. But I'm pretty sure we've been having good, except for me in class yesterday morning, we've been having pretty good with the internet people. So should be good. Make sure you're studied up and you're really ready to go. And make sure you're not planning on doing anything that I would disapprove of. Make sure you take the test. It's a good evaluation for yourself to see how you're doing. Don't forget to send me a picture of yourself if you want that extra point on that exam. And I need it before class begins or before the test begins. But try not to wait till the last minute. It's too many things for me to have to deal with on that one night. Any questions, Mikhail?
Can I send the pictures to you right now?
You sure can.
Okay.
Okay, well then, good night, folks, and I will see you either tomorrow night or on Monday, or in class tomorrow morning, whichever comes first.
Good night, Professor.
Good night.
Good night, Professor.
Okay.
Bye-bye. Bye-bye.
Good night, Professor.
Bye-bye.
Good night, Professor.
Bye-bye.